Good afternoon, geometry students. I am super happy to be doing another notes for you. It has been several weeks since we've talked about geometry, and I'm very excited to see you soon. I've missed you the last few months, and I hope that you've been doing well. We are going to be working our way through the second half of our geometry book, and as you probably recall, we finished up with chapter 6 right before you left for quarter 2 classes, and so we're going to be picking up with the beginning of chapter 7. I am going to try videotaping these notes from a more forward-facing position. I had tried going at an angle before so it could track me going back and forth on the board. But I'm thinking that this might work better for you, even though we'll have a little bit less space for me to write in. The information will be more head-on, so hopefully it'll be easier for you to see. Okay, so at the top of your paper, go ahead and write 7.1 angles of polygons. So 7.1 angles of polygons. And again, all you need to do notes is a piece of paper and a pen or pencil, and we'll go ahead and get started. So the whole chapter 7 is about different kinds of polygons and how to work with them. We're going to start off kind of defining what is a polygon and what is not a polygon. So a polygon is a closed figure, and it has to be formed by line segments called sides, and each side can only intersect at exactly 2 other sides. So for example, this would be an example of a polygon. It is a closed figure, it is made out of segments, and it only intersects 2 other sides. Another example of a polygon might be this kind of a shape. Now, in the first case, we're dealing with something we call a convex polygon. And almost all of the polygons in this chapter are going to be convex polygons. But there is also another type of polygon called concave. That is kind of like when one of the figures caves in on itself. And the way that you can see that that's happening is if you draw a line through a side, it can end up going through the figure. If a line that is traced along the side of the polygon goes through the figure, then it is called concave. Now, I'm wondering if you can think about why this would not be a polygon. So we're going to write here, not polygons. Why would that shape not be a polygon? This shape would not be a polygon because it's curved. It's not just made out of straight edges. Okay, let's look at this shape here. Why would that shape not be a polygon? In that case, it wouldn't be a polygon just because it's open. A polygon needs to be closed. This one's a little bit harder to see if we draw an hourglass shape. The reason that this one is not a polygon is because it intersects more than 2 other sides. If we look at this pink segment here, it's going to touch 3 different sides. 1, 2, and 3. Actually, it looks like it touches 4 different sides. So that would not be a polygon because in a polygon, each side can intersect only 2 other sides. Okay, so this is kind of a definition of what is a polygon, what is not a polygon. Now we're going to talk about different types of polygons, and we're going to do a little chart here. Many of these names you've probably already heard of, but this is a little bit of a review. We're going to talk about the names and also some features at the same time. We're going to start off describing a triangle, and for each of these items we want to write down how many sides that shape has, the number of triangles in that shape, and then the sum of the interior angles. Sum of interior angles. Okay, so a triangle obviously has 3 sides and 1 triangle, and I hope that you remember from last quarter that a triangle has 180 degrees on the inside. So the sum of the interior angles would be 180. Okay, let's do the second row. The second row with a quadrilateral a quadrilateral would have 4 sides. And if you just draw, any random quadrilateral, you can see that there would be 2 triangles inside it. So the interior angles would be 180 for the first triangle and 180 for the second triangle, or 360 total. All right, I'm just gonna do the next few rows kind of quickly here because you can just copy these down. If you need to pause the video or take a screenshot, please feel free to go ahead and do that. But we want to be looking for kind of a pattern, and we're gonna come up with a formula that we can use to find the sum of the interior angles of any size polygon. Okay, so these are the names for the different shapes. If we have 5 sides, it's a pentagon. 6 sides is a hexagon. An n-gon is what we call something with n sides. Can anyone see the number of triangles that would be in an n-gon? If you look at the pattern here, you can see that in each case we're subtracting 2, so we would just write n minus 2. And then you can see in the last column, we're taking this number times 180. So 1 times 180 is 180, 2 times 180 is 360, and then this last column would just be n minus 2 times 180. So there is a formula that tells us the sum of the interior angles of any sided polygon. And that is the formula right there. I'll write it down below just to kind of, or actually, I think there's a little bit of room off to the right here. The sum, S, of the interior angles of an n-sided convex polygon is n minus 2 times 180. So if you just want to add up all the angles inside a polygon, all you need to do is use this formula right here. And we'll do an example of that in just a moment. But before we do, I also want to tell you how to find the measure of one angle. So the measure of one angle in a regular polygon. Now remember that regular means that all the sides are the same length and all the angles are the same length. So we would just take this formula right here and divide by how many sides we have. Now, I'm gonna leave those 2 formulas up on the board for you, and then I'm gonna do a couple examples with some actual numbers to make it a little bit easier for you to see what's going on here. All right. So let's go ahead and take a look at a 10-sided figure. So example 1, we want to find the sum of the measures of the interior angles of a decagon. Deca means 10, so like a decade is 10 years, a dime is 10 cents. So if we wanted to find the sum of the measures of an interior angle of a decagon, that means that n is 2. So the sum of all of them using my formula, I would plug in, that means that n is 10. I don't know where I got the 2 from, probably here. So decagon means 10. So I would do 10 minus 2 times 180, which is 8 times 180, or 1,440. So all 10 angles of a decagon would add up to 1,440. If we wanted to know the measure of just one of them, so the measure of one interior angle, we would just take 1,440 and divide by 10 to get 144 degrees. So each of the angles is 144 degrees, and if you add up all 10 of them, it would be 10 times that. Okay, so that was example number 1. Let's go ahead and do, I don't know, maybe 1 or 2 more examples. Example number 2. I'm going to show you a quadrilateral. And we're going to write expressions for each of the angles here. So we want to think about what we know about this situation. We can see that we have 4 angles or 4 sides. So we know the sum has to be 4 minus 2 times 180, or 2 times 180, or 360. So all of these angles have to add up to 360. So I'm going to take all the angles I see inside the shape, add them up to 360. When I combine all of my x's, I get 32x. And when I combine all of my numbers, I get 8. Then I'm just going to solve the equation using opposite operations. So I'll subtract 8, and then I'll divide by 32, and I'll get that x is 11. Now, if we wanted to find the measure of each angle, we would just plug in 11 for x. So for example, that would be 55. And this would be 11 times 11, which is 121, plus 4, which would be 125. Okay, there is another type of example that's very similar, but not quite exactly the same. So let's take a look at that. This will be example number 3. For example number 3, it says the sum of the measures of the interior angles of a convex polygon is 4,500. Classify the polygon by the number of sides. So what they're doing here is kind of the opposite of the other problems. They're telling you what the sum of the measures of the interior angles adds up to, and then they want you to find how many sides there are. We can still use this formula to do this. So it says here that the sum of the formula, that the sum of the angles is 4,500. So I'm going to set 4,500 equal to n minus 2 times 180. Then I can divide both sides by 180. When I do, I get, this cancels out here, and I get 25 equals n minus 2. And using my opposite operations, I would get that this is a 27-sided figure. So you can use the formula either direction. You can take the number of sides and find out the sum of the interior angles, or you can take the sum of the interior angles and find out the number of sides. Now, there is another example that I could give you that is really long, writing out this huge chart, and it would take us forever. It would probably add about 6 minutes to this video. So instead of torturing you and taking you through all of that, I'm just going to tell you one more formula that you can use, and that is the sum of the exterior angles of any polygon is equal to 360 degrees. Now, again, if we had several minutes, or if you're interested during class sometime, I could take you through the proof for how we can prove this is true. But it's kind of weird. So, for example, a triangle that only has 3 sides, the exterior angles add up to 360. If you had a 100-sided figure, the exterior angles would also just add up to 360. So no matter how big or small the figure is in terms of its number of sides, the degrees for the exterior angle is still going to be 360. Okay, so for example, let's do example number 4. It could say, what is the sum of the exterior angles of a heptagon? Now, heptagon means 7 sides, but you don't actually need to know that, because any figure, no matter how many sides it is going to have a sum of exterior angles of 360. So it really doesn't matter what the number of sides is, the answer will be the same. Okay. Let's see here. I'm just thinking if there's anything else that you need to know. Let's just do one other example, I guess, example number 5. So example 5, let's say that we have a figure that looks like this. And in this particular figure, we're labeling the exterior angles. So 75 degrees, 80 degrees, 1.5 degrees, x degrees, and 105 degrees. In this particular situation, does anyone have a thought about what equation we would set up for to solve for x? So I know that the exterior angles have to add up to 360. So what I can do is I can just add up all these angles. So 80 plus 1.5x plus x plus 105 plus 75 all has to add up to 360. Then I can combine my x's. So 1.5x plus 1 more x is going to be 2.5x. And then if I add up all these numbers, 80, 105, and 75, I'm going to get 260. Then, of course, I want to do my opposite operations. So I'll subtract 260. I'll get 2.5x equals 100. Then when I divide by 2.5, I get that x is 40. So that's how I would solve that problem. Well, I am super proud of you guys for taking these notes. If you are interested in doing extra well in geometry, doing the notes will be really helpful to you. We won't have time to really do nearly as many examples of these for notes in class, but we will go over all of the homework problems together. So go ahead and get started on your 7.1 practice A, practice B, and puzzle time. And remember that we're just doing odds. Thanks, guys. Bye.